So hello, and welcome to the last topic on the GCSE course on quite a lot of different things really, but focus mostly on the idea of and examples and applications of reversible reactions. So the first thing to look at, probably very importantly here, is what is a reversible reaction? So a reversible reaction, pretty much as this name suggests, is one that can be performed in both directions, so both forward, going from the reactant to the product, as in any other reaction you've learned so far, and in reverse, in which the products are converted back to the reactants. So firstly, looking at an example that you will have seen in the acids, bases and salts topic, no doubt, this one, hydrochloric acid and sodium hydroxide going to sodium chloride and H2O. Now this is an irreversible reaction. It's called that because it will only realistically go in one direction. If you mix salt and water together, you aren't going to get a mixture of hydrochloric acid and sodium hydroxide. However, this, with that little symbol in there, is an example of a reversible reaction. So nitrogen and hydrogen reacting together to make ammonia. And that's actually an extremely important reaction, and we'll look more into that later on. But for now, just remember that that's an example of a reversible reaction, which is a reaction that can go both forward and in reverse, and that little thing is the symbol of a reversible reaction. Now, when we say a reversible reaction takes place, we're not saying something like the reaction's going to convert all of the reactants to the product and then it's going to go back. No, rather every reversible reaction will reach a state we can call equilibrium, and that's the state at which there are no further changes in concentration. So the concentrations of all the chemicals in the mixture past that point stay the same. Another way we can learn this, and perhaps a more accurate way to learn this, is the reactants are converted to the products at the same rate the products are converted back to the reactants. What that effectively means is that if you have a reaction mixture at equilibrium, individual particles are still reacting with one another. It's just that the reactants are reacting to create the products at the same rate that the products are reacting again to make the reactants. So effectively, there's no change in concentration. We wouldn't observe anything and the concentrations will remain the same. Another important thing about this is that the point of equilibrium doesn't have to be the point where there are equal amounts of reactant and product present in the mixture. You can have more reactant when it reaches equilibrium. You can have more product. What matters is that there is no further change to the system and its concentrations as a whole, and we wouldn't observe any change in those concentrations. That's all in this video. In the second of these 4 videos now, we're going to be going back to that reaction earlier I said was very important, nitrogen and hydrogen making ammonia, and that is called the Haber process.